All right, let's just jump right in. We throw around this term AI learning all the time, right? But what are we really talking about? It sounds a lot like, understanding, reasoning. But the truth is, what's happening inside these models is something totally different. It's a world of pure math that's, believe it or not, both way simpler and way stranger than you'd imagine.
And this gets us right to the heart of the mystery, something we've all seen. 1 second, an LLM is a flat-out genius, cranking out perfect code or beautiful poetry. And the very next, it's just making stuff up with this unshakable confidence. How is it possible to be so brilliant and so baffling at the same time? Well, that's the puzzle we're going to solve today.
So, first things first, we've got to get our language right. When we say an LLM learns, it's not at all what you and I do. There's no aha moment, no real insight or understanding going on. It's all about mimicking patterns it's seen before. It's a series of mathematical procedures that adjust billions of tiny little knobs or parameters. It is a fundamentally different kind of thing.
Now, for this whole mathematical dance to even begin, it needs a starting point. I mean, before a machine can get better, it has to have a way of knowing how bad it is. It needs a score for failure. That score has a name. It's called a loss function. The easiest way to think about it, it's just like a golf score. It's this single number that basically tells the model, hey, you're this far off. The higher the number, the worse you're doing. So the entire, and I mean entire goal of training an AI is to get that one number, that loss, down as low as it can possibly go. Ideally, all the way to 0. But here's the thing. You can't just make up any old scoring system. A really good loss function has to play by 3 rules. First, it's got to be specific. Measuring something concrete like, did you guess the next word right? Second, it has to be computable. Something a computer can do over and over, billions of times, without breaking a sweat. And finally, and this is the big one, it has to be smooth. And that third rule, smoothness, it is absolutely the secret sauce. It's the most critical part, and maybe the hardest to wrap your head around, but without it, the whole learning process just completely falls apart. So what on earth do we mean by smooth? Well, picture a gentle hill with a nice, continuous slope. When you take a step, your altitude changes just a little bit. Now, think about a staircase. That is not smooth. You're on one level, and then bam, you drop to the next. For an AI to figure out which way is down, which way is better, it needs that gentle, continuous slope, not a clunky staircase. And this brings us to a really, really important point. This whole scoring system couldn't care less about what's true or what's false. It only cares about one thing, matching the patterns it saw in its training data. So if a lie or a dumb mistake is a super common pattern all over the internet, guess what? The model actually gets a better score for repeating it. And that is why they can be so confidently, fantastically wrong. Okay, so this leads to our next clue. The model has its score for being wrong, and it's got this nice, smooth landscape to work with. So, how does it actually find its way down the hill? The answer is a clever little algorithm called gradient descent. This is the absolute workhorse of AI training. It's the engine that figures out exactly how to tweak those billions of little knobs, just a tiny nudge here and a tiny nudge there, to make that loss score go down. And the process works pretty much like a ball rolling downhill. Imagine you just drop a ball anywhere on that huge, hilly landscape of possibilities. All you do is look right under the ball, figure out which way is downhill from that exact spot, and just give it a little push in that direction. And then you do that again, and again, and again. Billions of times, until the ball eventually settles down in a valley somewhere. Now, you can think of this as a greedy algorithm. It's like you're on that same hill, but you're in a fog so thick you can only see your own 2 feet. You can tell which way is down for the very next step you take, but you have no clue if a much, much deeper valley is just a few feet away. Why do it this way? Well, because checking every single possible path is just computationally impossible. The step-by-step foggy approach is really the only way it can be done. So let's recap. We've seen how an LLM scores itself and how it makes itself better. We've looked at the machinery. But what's wild is that all of this incredibly complicated stuff, the loss functions, the gradient descent, all of it is built to do one surprisingly simple job. So what is it? What's the one task that sits at the very core of every single thing a large language model does? Let's just watch it happen. The model gets an input, the. Its only job is to guess what word comes next.
It predicts cat. Okay, now the input is the cat. What's next? It predicts sat.
Now the input is the cat sat. Again, it predicts the next word, on. It's just building one word at a time.
And finally, the cat sat on the... So what's the most statistically probable word to come next based on all the text it's ever seen? And that is it. That's the whole secret. The LLM's only real job, its one and only purpose in life, is to predict the next word. Seriously, every single amazing, complex, and yeah, sometimes totally weird thing it does, writing poems, spitting out code, answering your questions, it all just kind of emerges from doing that one super simple task just trillions of times over on a mind-boggling scale.
Okay, so now that we're in on the secret, we can go all the way back to that paradox from the beginning. Once you understand that an LLM is just a fancy next word prediction engine, it explains everything, both its incredible abilities and its spectacular failures. It's a pattern matcher, not a thinker.
Think about it. Ask it to write some code in a really popular language, say Python, no problem. It's seen millions of examples, the patterns are strong, and it does a great job. But then ask it to write in some obscure language that it's barely seen any data for. What happens? It starts to just make things up, confidently using patterns from other languages that are completely wrong. This becomes crystal clear with logic puzzles. Give an LLM a famous puzzle, one that's all over the internet. It'll solve it perfectly because it's just seen that pattern before. But change the rules just a tiny bit. Give it a problem it's never seen, and it completely breaks down. It often just gives you the answer to the original puzzle. It's not reasoning, it's just recognizing and repeating a pattern. So what do you do with this information? Well, it's basically your user manual for these tools. Use them for common stuff where you know the patterns in the data are strong, but be really, really skeptical when you give it new or strange problems. And please always, always double-check anything important that comes out of it. Just keep chanting the mantra, it's a pattern matcher, not a reasoner.
Look, knowing the difference helps you get the most out of these incredible tools while staying out of trouble. But it does leave us with a massive, fascinating question. This ridiculously sophisticated pattern matching has gotten us this far, which is amazing. But what comes next? What is that leap from this to what we might call true AI reasoning? What does that even look like?